Tesla marked a major turning point in NVIDIA's history because it introduced unified shaders, allowing the GPU to handle graphics tasks more flexibly than earlier designs. Compared with older GeForce architectures, Tesla could process different types of workloads using the same pool of cores, which improved efficiency and opened the door to modern GPU computing. It was also the first NVIDIA architecture to fully support CUDA, enabling developers to use the GPU for scientific, engineering, and professional applications. In gaming, Tesla-powered cards such as the GeForce 8800 series delivered a huge performance leap over previous generations and quickly became highly influential. Compared with later architectures, however, Tesla lacked dedicated AI features, ray tracing hardware, and the power efficiency improvements that would arrive in subsequent years. Even so, it established many of the foundations that modern NVIDIA GPUs still rely on today, making it one of the company's most important architectural breakthroughs. Fermi represented a major evolution from Tesla by focusing heavily on both gaming and professional computing performance. Compared with Tesla, Fermi offered a more advanced CUDA architecture, improved double-precision performance, and stronger support for complex workloads such as scientific simulations and 3D rendering. NVIDIA also introduced technologies like ECC memory support for certain professional products, making Fermi more attractive for data centers and research institutions. In gaming, cards such as the GeForce GTX 480 delivered significantly higher performance than many Tesla-based models, although they also became known for high power consumption and heat output. Compared with the later Kepler generation, Fermi was less efficient and required more electricity to achieve its performance levels. Nevertheless, it played a crucial role in expanding the GPU beyond gaming, helping NVIDIA establish a stronger presence in professional computing and laying important groundwork for future high-performance architectures. Kepler shifted NVIDIA's focus toward efficiency while still delivering strong performance gains over Fermi. Compared with Fermi, Kepler achieved higher performance per watt, allowing graphics cards to run faster while consuming less power and generating less heat. NVIDIA also introduced GPU Boost, which could automatically increase clock speeds when thermal and power conditions allowed, giving users extra performance without manual tuning. Popular cards such as the GeForce GTX 680 showcased how much more efficient the architecture had become. Kepler also expanded NVIDIA's presence in supercomputing and mobile graphics, making it more versatile than Fermi. Compared with the later Maxwell generation, however, Kepler was still less optimized for energy efficiency and gaming workloads. Even so, it represented a significant step forward by balancing performance, power consumption, and scalability more effectively than its predecessor, helping NVIDIA strengthen its position in both consumer and professional markets. Maxwell focused on extracting much more performance from every watt of power. Compared with Kepler, Maxwell delivered major efficiency improvements, allowing GPUs to achieve strong gaming performance while consuming significantly less electricity. This made cards such as the GeForce GTX 970 and GTX 980 particularly popular because they offered excellent performance, lower heat output, and quieter operation. NVIDIA also improved memory compression techniques, helping games run more smoothly without requiring dramatic increases in memory bandwidth. Compared with the earlier Fermi and Kepler generations, Maxwell felt more refined and efficient, making it attractive for both desktop and laptop gaming. However, compared with the later Pascal architecture, Maxwell lacked support for newer technologies such as high-speed GDDR5X memory and the large performance jump that Pascal would introduce. Even so, Maxwell became one of NVIDIA's most successful generations by delivering a strong combination of efficiency, performance, and practical everyday gaming value. Pascal brought one of the largest performance jumps in NVIDIA's consumer GPU history. Compared with Maxwell, Pascal offered substantially higher performance, better power efficiency, and support for faster memory technologies such as GDDR5X. Built on a more advanced manufacturing process, cards like the GeForce GTX 1080 and GTX 1070 delivered impressive gaming performance while still maintaining relatively efficient power consumption. Pascal also became a major driver of virtual reality gaming because it could handle demanding VR workloads more effectively than previous generations. Compared with older architectures such as Kepler and Fermi, the improvement in both speed and efficiency was dramatic. However, compared with the later Turing generation, Pascal lacked dedicated hardware for real-time ray tracing and AI acceleration. Despite that limitation, many gamers considered Pascal one of NVIDIA's strongest generations because it delivered excellent performance, strong efficiency, and long-lasting value across a wide range of games and applications. Turing introduced a new era for NVIDIA by adding dedicated hardware for both ray tracing and artificial intelligence. Compared with Pascal, Turing GPUs included RT cores for real-time ray tracing and tensor cores for AI-powered features such as DLSS, allowing games to achieve more realistic lighting, reflections, and image reconstruction. Cards like the GeForce RTX 2080 and RTX 2070 showcased these new technologies and marked the beginning of the RTX branding that continues today. In traditional rasterized gaming, the performance improvement over Pascal was noticeable but not always as dramatic as previous generational leaps. However, the addition of ray tracing and AI acceleration made Turing fundamentally different from earlier architectures such as Maxwell, Kepler, and Fermi. Compared with all previous generations in this script, Turing was the first to combine strong gaming performance with dedicated hardware for next-generation visual effects and AI workloads, setting the direction for NVIDIA's future GPU development.